Right class, welcome back to the next lesson on cantilevers. Notice the cantilever is fixed on the right hand side and the beam goes to the left. Just a touch different, not much, pretty much the same. And we have a point load sitting at an angle. And of course we're going to resolve it into its components. We have a UDL there, we have a point load there. And note, it says the mass of the beam is 46.2 kilograms per meter. Okay, so before we can start, what are we going to do? We're going to have to work this mass of this beam into a load on the beam. Okay, and that's what we're going to do. Alright, so the mass per meter. Alright, let me just see here. So the mass of the beam, so we're going to need to work that into a total weight of the beam. Okay, so the weight of the beam, W, okay, is equal to 46.2 kilograms, okay, and of course we need to multiply that by 9.81 to convert it to 9.81 meters per second squared. So that there will convert it to newtons, and of course we need to divide it by 1,000, and it will give us so many kilonewtons. Okay, but that there is kilonewtons per meter. So let's work it out. So it is 46.2 times 9.81 is equal to, divided by 1,000, and I'm going to say it is 0.45 kilonewtons per meter. Okay, so there's the mass times G divided by 1,000 gives us so many kilonewtons per meter. Why did I divide by 1,000? Because I want to bring this in line with all of that over there. If I didn't divide it by 1,000, the answer would have been in newtons per meter, and if I use it with this here, it will be wrong. Okay, it will be 1,000. It will be 1,000 bits out. Right, now that there is actually a UDL. Okay, now I can either spread that 0.45 kilonewtons per meter over the whole beam, or, did you hear the word or I can convert it to a point load. Okay, and just by the way, in structural terms, this here is little w. If I convert it to big W, we'll see later. If it weighs 0.45 kilonewtons per meter, I can convert it to a point load, and I multiply it by the full length of the beam. So I'm going to say 0.45, the value I got in my calculator, and I'm going to multiply it by 345 times 7. So I'm going to say times 7 is equal to, so it's going to be a point load of 3.17 kilonewtons, and it's acting downwards dead at the center of the beam. Okay, alright, so I'm going to put it in there. Let me just change something here. I'm going to put it on my beam, and it's going to be acting dead in the center over there. So it is somewhere sitting. I'm just going to do this like so, and of course if that's 2 meters, that's 2 meters, so in the middle here it will be 1.5. so I'm just going to do this here. I'm going to say so. Try and get it nice and horizontal. Okay, so there's my point load, which is the weight of it, 3.17 kilonewtons, sitting in the middle there. So, and why is it in the middle there? Because the weight always acts to the center of gravity of an object. So that's 2 and 2, so it's stayed in the middle there. So, right, so now we can take moments for the beam. Okay, let me just give it a nice darker color here so you can read it easier. Right, I'm going to assume forces and directions. So there will be my VA, and of course the beam is wanting to turn anti-clockwise with respect to point A, so therefore there's got to be a momentary action sitting in a clockwise fashion, okay? And this force here, because as an angle, we got to resolve it into its components, and I'm going to do this. So I've got a force sitting like so, and I've got a force sitting like so. Okay, right. So if that's 60, so that's going to be 16. That's going to be 60 there. So that's going to be 16 cos 60, 16 cos 60. And that's going to be, I want to 16 sine 60. Just okay. I'm squeezing like that over there. Right. Let's take moments. So I'm going to say, I'm going to take them to the moments first. So the sum of the moments about A is equal to 0. Right. Moment at A is positive, so it's going to be plus. Right. Notice there, all the loads on the beam will be anti-clockwise with respect to point A. So it's minus. I'm going to do the point clouds first. So now remember, these two forces here act at that point over there. Okay? They're actually acting, maybe I should just draw it in there so you can see it. It's actually sitting over like so. And it's sitting like so. Okay? Sitting there like that. Right. So, I'm going to do that force there, and I'm going to take that force and work my way to the right. That one there is 16 sine 60. So, 16 sine 60. Remember, that's just the force, okay? The lever arm is the length of the beam, which is 3, 4, 5, 6, 7, okay? Minus 48 times 2, 48 times 2, minus 12 times 3. Remember, that's just the force, and the lever arm acts to the center. It happens to be at the same position as the weight of the beam. Ne? It just happens to be at the center. So it will be 12 times 3 times 1.5 plus 2. So it will be 3.5. Okay. Alright, so that's done. So we got that one there. We have, and we must still take the weight, of course. Almost forgot about the weight. It's 3.17, and it's also 3.5 meters away from point A. And that force there, will that force have any moment effect about A? No, it won't, because if it's sitting over there, it's acting to the point of rotation, so it has no moment effect about A. So there's no more. So we got 1, 2, 3, 4. Let's see, 1, 2, 3, 4, 5. So it's 1, 2, 3. I'm just checking. It's equal to 0. Therefore, moment at A is equal to. Let me pause it there while we work that answer out. While I'm pausing it, just try and work out the answer. Okay, people, I did the calculation. I checked it. It should be correct. The moment at A is 330.09 kilonewton meters. Not kilonewtons. Not kilonewtons per meter. That's UDL. Okay? Kilonewtons is the force of reaction. It's kilonewton meters. And because our answer is positive, it means that our assumption that the reaction moment is going clockwise with respect to A is in fact correct. And I show it as such. Right, I'm going to sum verticals to find VA. So I'm going to say the sum of the forces in the vertical is equal to 0. Right, I've got VA, which is positive, going up. and of course minus all the loads acting on the beam. So it's minus 16 times 60. I'm starting from the left going to the right. Minus 48 minus the weight of it minus the UDL, which is the value of it times its length, because it has the value of 12 k's per meter, so it's minus 12 times 3, and I think that's all of it, and it's equal to 0. So it's 1, 2, 3, 4, 5, 1, 2, 3, I'm checking, so therefore I'll do it over here for space. So VA, let me just pause this for a second and get that the correct answer. Okay people, VA, I got that to be 101.03, 101.03, and it's reaction, so it's kilonewtons, not kilonewton meters at the moment, okay? And because the answer is positive, it means that VA is upwards is in fact correct. Right, I'm going to sum horizontals. It's HA, sorry, my apologies, I forgot to put HA in. HA is over here. I am going to assume it to be to the right. Why am I assuming HA to be to the right? Because I have a force going to the left. Okay. If I assumed HA going left, if I did my calculation, HA would have been a negative value. So I'm assuming it to be the right. So I'm going to say the sum of the forces in the horizontal is equal to 0. So I've got HA minus 16 cos 60 equal to 0. Therefore, HA is equal to 16 times cos 60. Cos 60 is exactly 8 kilonewtons, 0.00 kilonewtons. It's a force, therefore it's kilonewtons, and because the answer is positive, it means that our assumption that HA goes to the right, is that the word there. People, let me just squeeze it in here somewhere. Let me just show you. Let's say you weren't sure, and I'm gonna make HA going to the left like so. Okay, let me assume that. Let's say I assumed HA going that way because I had loads of forces. I didn't do it, so I wasn't sure, so I guessed it to go left. So now I'm going to say the sum of the forces in the horizontal is equal to 0. That will be minus HA. Why minus? Because I'm assuming left. Minus 16 cos 60 is equal to 0. Right. So when I sum forces there, when I solve for HA, I find that HA is equal to, HA will be equal to minus 8 kilonewtons. Okay. But what does the minus sign mean? The minus sign means that my assumption that HA was to the left is incorrect. So in fact, HA does go to the right. So whether you make a wrong or right assumption, the sign in the answer will tell you which way the direction must go. Okay? So if you assume HA left, that will be your calculation. If you assume HA to the right, that will be your calculation there. Okay, people. I think that's all I'm going to do for cantilevers. This cantilever had a load at an angle. I had to resolve forces into their components. And the beam also had a mass of 46.2 kilograms per meter, which I converted to a weight, and I divided by 1,000 to give us so many kilonewtons per meter. I multiplied that by 7 to give us the total load. Remember, it weighs so much per meter. The beam was 7 meters long, so the total weight of the beam is actually 3.17 kilonewtons, and it acts to the center of the length of the beam, sitting over there. Okay, and then I took moments and some vertical forces. Okay, people, that's all for now, and I will see you in the next lesson.